Okay, so you need the white paper you picked up and your FRQ booklet. And we are looking at FRQ4. So we're going to go through FRQ4 that you did on the mock. Then we're going to look at some of the trig identity stuff. And then we're going to get to those yellow papers, okay? Now, I will tell you overall, FRQ4 stunk up the room for everybody, all right? So I saw some people this morning like trying to hide their books so their neighbor, look, everybody's looks like trash. Just open it up and let's figure out how to fix this, okay? I don't know, we'll figure it, maybe. I'll just say 3 is like really, really good on that one. Okay. All right, now listen, but I know you can get more, so we have to make sure we're paying attention to how to get more. You're talking and not listening. All right, so you can write on both the paper I gave you and that. Obviously on the actual booklet, you'll have way more room to write. But FRQ4 comes with an additional set of directions that we need to make sure we read and understand. They will look identical to this when you get it, okay? So you should read through them again, but let's talk about them. So unless otherwise specified, which I can't imagine that it would be on this, but the domain of function f is assumed to be the set of all real numbers. So they're telling you that so that they don't have to say it on each question. And it also says that angle measures for trig functions are in radians. Well, that's good because that's all we've talked about, right? I mean, we understand the degrees a little bit just to make sense for us, but everything is done in radians. Solutions must be real numbers, so no imaginary stuff here. And then this is important, determine the exact value of any expression that can be found without a calculator. And then they give us some examples. So if they ask me for the cosine of pi halves, I have to actually give the answer to that. What is the cosine of pi halves? 0, yes. And then the sine inverse of 1, like that's something I have to actually give. Just testing you there. But let's talk about this one, because that's probably going to be the exact example they give, but just so you understand the log stuff. Because there is sometimes we get logs that we can't do anything with without the calculator, but this one we can. So log base 2 of 8. Now, if I had log base 2 of 2, that'd be great. Log base 2 of 8, I don't know what that is off the top of my head, but I can rewrite this as log base 2 of 2 cubed. That's a 3. 2 cubed. Y'all agree with that? Because 8 is 2 cubed. Then what can I do with that 3? He gets to come out front, right? So that gives me 3 times log base 2 of 2. And log base 2 of 2 is just 1. So that gives me 3. Okay? So not okay to leave log base 2 of 8 because we can get it to 3. Not every log you get, you will be able to manipulate like that. And we'll look at one of those when we get there. Then, unless otherwise specified, which again, I can't imagine that they would say that on here, combine like terms and basically reduce everything. Okay, like you can't leave them like what it shows right there. Remember on FRQ3, if we have 2 over 4, we can leave that and it's fine, right? I suggest you leave it. Here, we can't leave 2 over 4, we need 1/2, okay? And then most importantly, show the work that leads to your answers. Because yes, you get a point for the answer, but you're not even you don't get a point for the work and a point for the answer, you get a point for the answer. But if your work isn't there, you're not getting that point, even if the answer is right, okay? Just like I've said many times, you can do it in your head, great, nobody cares, you're still not getting the point. So you got to show your stuff. All right, let's look at what we got here. The functions g and h are given by this. It's telling me I want to solve, and it tells me g of x is 10. So I'm going to have e to the x plus 3 power equals 10. Okay. Then to get an exponent or really, or a variable out of an exponent or really exponent out of the exponent no matter what, I have to do that with a log. What log is related to e? Natural log. So I'm going to take the natural log of both sides. So that gives me the natural log of e to the x plus 3 equals the natural log of 10. So this x plus 3, that whole exponent gets to come out front. And then the whole reason we wanted natural log is the natural log of e is 1. So that left-hand side stays x plus 3. Natural log of 10 is natural log of 10. It is different than log base 2 of 8. I can't manipulate that to get a number. So there are times where it's fine to leave it in log form. Okay, there were quite a few of you that got here, and then things went bad from here. Trying to get x by itself, so x equals the natural log of 10 minus 3. It does not equal the natural log of 7. Shame on you. You know you can't do that, right? I didn't do it. And then that is your answer. We all good on that? That's 1 point. If you didn't get that point, see if you can figure out what went wrong where. Okay? Any questions? All righty. Let's look at this next one. I've got arc sine of x over 2, and that's equal to pi fourths. Okay, arc sine is the exact same thing as what? Inverse. Sine inverse and arc sine are the exact same things. It's just two different ways to say it. All right. So if this is the sine inverse, and I want to do the inverse of that, that's just sine, right? Sine and sine inverse are inverses of each other. So I'm going to take the sine of both sides. So on the left, the sine of the arc sine. Now, if this was a number right here, they don't always just cancel each other out, but they do. It's a variable. It's how that works there. So this is x over 2 is equal to the sine of pi fourths. Okay. Everybody with me so far? What is the sine of pi fourths? Square root of 2 over 2. Good. X over 2 equals square root of 2 over 2. So what does x have to equal? Square root of 2. So algebraically, I'd multiply both sides by 2 and cancel it out. But just looking at it even without algebra, if something over 2 equals the square root of 2 over 2, then that something has to be the square root of 2, right? What questions do you have? Again, if you didn't get that, figure out where things went awry. Well, there you go. That's something. What questions? Yeah, I will say this also. FRQ4 is probably the most challenging as far as this kind of stuff goes. And when you start it, you have 15 minutes left after a long test. And some of y'all are stressed out because you're about to have to inhale your food and go take an APPS exam. All right. So, you got to make sure you don't psych yourself out. You can take a deep breath and get through this. All right. Now let's look at B. Here's the main difference between A and B. Those said solve. This says rewrite. I'm not solving for anything. And if you don't have that in your mind, that leads you to do really strange things sometimes. So we're going to rewrite j of x as a single log with base 10. I still find it weird that they actually write the 10 because you will never see that anywhere else. Without negative exponents in any part of it. And your result should look like this. It even tells you what you're going for. You're going for log base 10 of something. Okay, so if you get x equals 5, then that's on you because that's clearly not what we're looking for here. So I'm going to start by rewriting this and cleaning it up a little bit as I write it. So I've got log base 10 of 8x to the 5th. So it just starts with a log. That's good. Plus, the next one is just plain old log. So log base 10 of 2x squared minus, but that one doesn't start with log. There's a 9 there. What can I do with that 9? Yep, throw it. Is that what you said? Yeah, throw it up in the exponent. That works. We get log base 10 of x to the 9th. Okay, so now I have log, log, log. If you are condensing more than 2 logs at once, chances are really good it's going to be some sort of quotient, which means I have a fraction. I suggest we do it all at once so we don't get lost in our signs here. So this is going to be a single log base 10. It's going to be a fraction. So I have 3 terms. I look at this first term. This first term is positive because there's no negative sign here. So that means the argument goes in the numerator, 8x to the 5th. Then this is positive, so that argument goes in the numerator. And then this is negative, so that argument goes in the denominator. Now I will say, quite a few of you got here, and you're not wrong, but you're not finished, because we can't leave it like this. Even though this has the same value, we have to simplify this all the way. So then this becomes log base 10 of 16x to the 7th over x to the 9th. And I'm still not done, because I can cancel 7 of these, or all 7 of those with 7 of those, and I end up with log base 10 of 16 over x squared. So if you got to one of these 2 steps but didn't finish it, then that's, you didn't get that point, but you do know what you're doing. We just have to finish it up, okay? And that's the main difference with FRQ4. And I had a question earlier today because somebody said, do I have to write log base 10 on all of them, or can I just stick it on there at the end? No, you have to write it on every single one. Your work has to flow, and you have to have like actual equal statements. Okay? Questions?
If it didn't say like it has to say log base 10, but we were still looking at log base 10,
yes, yes. I think honestly, even on this, if you just wrote log and you didn't put the 10 there, technically that is still log base 10, so it'd probably be fine. But if it shows it like, I'd write it. I do think it's strange. It's probably the only time you'll ever do it, because before when you saw it, you didn't do it. I know you won't do it in calculus, but whatever. But yes, it's still the common log. That didn't change. Anything else? All right, so now we are going to rewrite k of x as a single term involving tangent x. Okay, so this is what we're going to review some after we do this. I'll let second period decide if we were going to do the FRQ first or the review first. I want to do the FRQ first. So if I have something that's squared, that means that I could possibly want my Pythagorean identities. Not necessarily for sure, but definitely a possibility. In this case, it actually would help me. So I'm going to have, so that's sine squared. So something you have to know that sine squared theta plus cosine squared theta equals 1. Like that's one of the ones you have to have committed to memory to be able to do all of this. Then I highly suggest, although I know some of you won't because you're stubborn, but you write down what you're trying to get to, and I'm going to show you why this matters in just a second. We're trying to get 1 minus sine squared. So 1 minus sine squared, if I have that, so if I take 1 and I subtract the sine squared over, that leaves me with cosine squared. So that's not that difficult. So I know that's why some of you are like, I can look at it and know that. Well, I know you can. I can too. But then here's where y'all make the mistakes. Is what if I had sine squared theta minus 1? Does that give me cosine? No, that gives me what? Sine squared, if I subtract 1 over here, I got to subtract that over there. That's going to give me negative cosine squared. You see that? And I promise you, the majority of you would miss that negative if you didn't write it down and try to relate it, okay? Myself included. Now, this is not what we're going for right now. This is what we're actually going for, but I just wanted to show you the why you would probably want to write it down. So here, since this is 1 minus sine squared, I can replace that with cosine squared. So that's going to give me cosine squared x over sine x times, and then secant is 1 over what? Cosine. Okay. And I don't know that I've seen this from any of you, but when I said 1 over secant is what? And you said cosine. And I said, yes, cosine. And we say those things and it's totally fine. Just make sure you're not leaving off the x's and the thetas. Because again, I don't think I have that issue with any of you. So that used to be big time issues that people have just kind of stopped doing. So just make sure you're putting your arguments there and we're good. All right, so now I can cancel this cosine with one of those. That leaves me with cosine x over sine x. And what is cosine x over sine x? Cotangent. And I don't want cotangent, though I want tangent, right? So that means this, my final answer is 1 over tangent x. Okay. Okay, questions at this point? All righty. So now you have 4 points. 1 for each one of those would have been 4 points. This last one's always going to be worth 2. Now, where those 2 points are or how those 2 points are distributed depends on the actual equation that they're giving you. But depending on the equation, and it didn't happen here, but one of them points can come just from the setup. And this says find all values in the domain of M that yield an output value of 0. Even if we hadn't done cosine inverse by now, which we had, or even if we hadn't done trig stuff by now, if you know you want your output to be 0, then there's no reason you can't write down cosine inverse of the tangent of 2x equals 0. If you didn't at least write that, shame on you. Now, and your whole family. And this, in this case, that didn't actually get you a point on this one. But if, again, a different equation, it could. So there's no reason to not put it down there and then worry about whether or not you know how to do it. Or if you're about to run out of time and you're like, I don't have time to solve all this. If you can at least set something up, that might give you a point. So you use every second that you have and you don't leave anything blank, okay? All right, so now let's see what we can do. If this was a number and not a variable, we'd work from the inside out, but it's a variable, so we have to work from the outside in, which means I need to get rid of that cosine inverse. What is the inverse of cosine inverse? It's cosine. Cosine and cosine inverse are inverses of each other. So I'm going to take the cosine of both sides. So the cosine of the cosine inverse, they take care of each other. And I get tangent of 2x equals the cosine of 0. Now, you got to be careful with 0. Because I can take the cosine of 0, I can also take the cosine inverse of 0. And so right now, you've got about 5 minutes left to test. Your brain really is mush, and you're probably hungry, okay? So you've got to think, I always take the sine, cosine, or tangent of an angle. That 0 has to be an angle. So I am right here. What is the cosine value right there? 1. Okay, so I've got tangent of 2x equals 1. Now, sort of. Now, this question here could be asked, like, what are all the values in the domain, like it says right there, or it could say all the values from 0 to 2 pi. And that's where we have to think about spinning more than once, you know, or half the time or whatever. But it didn't, so it doesn't have the 0 to 2 pi. So I don't have to worry about that right now, but we will go back and look at some of those. But all I have to think about is when is tangent positive? First quadrant and third. Okay. So that means that 2x, whatever's inside, I still got to keep that, is equal to what angle gives me a tangent value of 1? Pi fourths. And then my third quadrant pi fourths? 5 pi fourths. Okay. Now, the way the points are distributed on this trig one, I'm going to take you through the rest of this a little bit differently than I did in the notes. Now, after I went back and I read all the scoring and how this works, because it asks for all of them, that means I need an infinite amount of them, so I need the k in there and all that stuff, right? But you can get one of your 2 points if you don't even understand the k stuff, all right? So if that blows anybody's mind, or if you mess up on the period or anything else. So right here, but you have to remind yourself, I'm not really done, right? Like, really, that's not really my answer. And you don't have to do it in 2 separate pieces. I'm just throwing this out there. Right here, I need x, so I'm going to multiply by 1/2. And that gives me x equals pi eighths and 5 pi eighths. And even though that's not really my answer, they give you a point for that. At least they have on the last ones. Now, can I guarantee all the points come out the same? No, but so then what I really want, and you go back to the 2x. So 2x equals pi fourths plus, now this was tangent. What's the period for tangent? Pi, plus pi times k, and 5 pi eighths, no fourths, sorry, you're going back to this one. 5 pi fourths plus pi times k. Okay, then we multiply that by 1/2. And this gives me x equals pi, oh my God, I can write and say the same thing. Pi eighths plus pi halves times k, and 5 pi eighths plus pi halves times k. That's why I had to put it back in here, and I can't just plop it in afterwards. Now, you can skip this whole step and like do it the quote right way, and that's fine. But if you're afraid you're going to mess something up, do them separately, and then you could still get that point there, okay? If that's even exactly what the last one looks like. You know, because we could have a lot of different equations down here at the end. It wouldn't have to be a trig one. What questions do we have? Anything? All right. So then you can put that stuff back in your folder for now. Grab your notebook paper. This is going to go on ISN page I think. What was that? Yes. And we're going to name this Trig Identities. I figured lined paper would probably be better for this. And I thought about having you write in your ISN, but some of you have wide ruled, some of you have narrow ruled, and some of y'all don't even write on the lines when they're there. So I was like, you know what? I'm just giving you notebook paper. So I'm going to do a lot of what we did on the first day of the lesson, but kind of in a little bit of a different way for some of it, and maybe not quite as much on some of it. So the first thing I want you to write is you're going to write sine squared theta plus cosine squared theta equals 1. Write that 3 times across. So that is this is the kind of the OG Pythagorean identity. Should make sense. It really just means y squared plus x squared equals 1. I don't think this one is necessarily difficult to remember. Whether sine or cosine is first really doesn't matter at all. Okay, so really just you're squaring the two and add them together. So I'm going to write something that I don't want you to write because then I'm going to take it back off. Because one of the things we did on day 1 is I wrote all the different kind of, not all of them, but a lot of different ways you could write it. And then I think in the end there was just too much stuff everywhere. But so don't write this. You can go back and write these in if you want. But what you could do under this so that you can understand what's happening is say, all right, well, cosine squared theta would be 1 minus sine squared theta, right? And then you could write the other versions of what's there. I wouldn't do that right now because I'm not going to give you time to do all that. But if that helps you kind of figure things out, or hopefully you just understand that you can do that when you need to, okay? But what we're going to use those other two for is to come up with the other two identities, because there's sums with tangent squared, secant squareds, whatever. Maybe you have the kind of brain that just knows them. Most of us don't. And so, and even though I know them, I still think through this process to make sure I haven't messed them up. Let's say that for some reason I needed a cotangent squared, okay? So cotangent is what over what? Cosine over sine. So if I want cosine over sine, if I look at this one, then if I divide that by sine squared, then I'd have that, right? So I'm gonna divide every single term by sine squared theta. Oh, yes, thank you. Yes, you do write this down. Thank you. That same thing happened earlier today. Everybody's just staring at me. I'm like, what are you? Oh, no, you can't write this one down for sure. Sorry. So then when I get sine over sine, that is 1 plus cosine over sine is going to give me cotangent squared theta. And what's 1 over sine? Cosecant squared theta. And then there's that identity. And just like with the first one, I can also do like cosecant squared minus 1 equals cotangent and all those other little versions. But like this is the main one that you can get from just taking this and dividing it all out. Well, what if I needed one with tangent in it? Then I would go through and divide every single one of these by cosine squared. So this will give me tangent squared theta plus 1 equals secant squared theta. Again, if you just know them and you have that kind of mind that these just make sense to you, you see some sort of pattern, that's fine too. But these are your 3 basic Pythagorean identities that you may have to rearrange after that to use however you need to use it. Okay. Any questions on how to come up with those? We good? Okay, so now skip a few lines in case you want to go back and write some stuff in there because you'll have plenty of room on this. And we're going to talk about your sum and difference identities. So let's say that I have sine of alpha plus beta. Now I have a few different ways for you to remember how to do this, but I did find this cute little video that has like a little story. And if you just sort of follow the story, I'll talk you back through the story as we write it down because it seems kind of silly, but I mean, hey, I think it does. I think it has its place. If it makes sense to you, that's all that matters.
This is the trigonometric love story of Sinbad, a handsome young man, and Cosette, a beautiful yet snobbish young girl. Once upon a time, in a land far, far away, lived a handsome young man named Sinbad. Sinbad was in love with a beautiful young girl named Cosette. Unfortunately for Sinbad, Cosette did not feel the same about him as he did about her. Spring arrived, and the local town hosted a dance. Sinbad asked Cosette to go with him. She did not really want to go, but alas, no one else asked her, so she agreed on one condition, that her curly-headed sister come with them. This was an acceptable compromise to Sinbad, because he had a rather ugly brother who needed a date. Arrangements were made, and since Sinbad was in charge of the date, he put Cosette in the front seat of the carriage with him, and he put her curly-headed sister and his rather ugly brother in the back. During the ride to the dance, Sinbad shouted to the crowd, bragging that his and Cosette's signs were the same. Here's how their date looked. Sinbad sat in the front seat with his beautiful date Cosette, and he put her curly-headed sister and his rather ugly brother in the back. The date finally ended, and Cosette was determined never to be seated with Sinbad again. Weeks later, the town hosted yet another dance, and once again, Cosette found herself in need of a date. Although she did not want to ask Sinbad, she knew he would say yes. Since she was in charge of the double date this time, she placed herself in the carriage up front with her sister and put Sinbad in the back with his brother. As they drove through the town this time, Cosette made sure everyone knew that their signs were not the same. This is what their date looked like this time. Cosette sat in the front with her curly-headed sister, and Sinbad sat in the back with his rather ugly brother. And that is the trigonometric love story of Sinbad and Cosette.
Okay, so here's how we connect all this together. All right. So when Sinbad was in charge of the date, Sinbad, so that's going to be sine of alpha, he sat Cosette in the front seat with him, cosine beta. Okay, sine of alpha, cosine beta. Sinbad and Cosette sitting in the front, and he's telling everybody their signs are the same. So this is positive, this is positive. In the back seat, he sat her sister and his brother. Okay, again, cheesy, but it works. Okay, so Sinbad sits up front with Cosette, and Cosette's sister sits in the back with Sinbad's brother. And you got to do the alpha beta thing, and the signs are the same, which means for alpha minus beta, it's the same. You just change the sign in the middle there. So sine alpha, cosine beta, minus cosine alpha, sine beta. All right, do you kind of see how the story goes with that? So then once you have that, you can skip a line or two just so it's not all crammed together. So then when Cosette asked him out, Cosette, or cosine of alpha plus beta, Cosette's like, I ain't sitting with you because I just need a date. And so this is Cosette, so cosine alpha, and Cosette's sister sits up front with her, cosine beta. The two of them are sitting in the front seat. And she's like, look, I don't know what he's been telling you, but our signs are not the same. This is plus, so this is minus. And then Sinbad had to sit in the back with his brother. Okay? You just think of it as a terrible love story. And then when you do cosine of alpha minus beta, then that gives you the same thing, but the sign changes. Okay. Everybody good with that? Now, there are ways, and we'll talk through this a little bit tomorrow, but like this, if we absolutely know this one, then we've got to be able to, we can know the rest. But really, if you know this, the love story of, or the semi-love story, I guess, of Sinbad and Cassette, then you can get this far. Okay, we good so far? Now we have a couple more left, but we're going to pick up here tomorrow. Okay.